The joys of the modern digital age. Now, as far as ages go, we've clearly entered into the Cambrian explosion of digital content. You see, we have plethoras of data out there on the internet. Books, music, videos, even your favorite TV shows are all available at the touch of a button or a finger to any device you want anywhere in the world. Now, think about this for a minute. I mean, we're talking about yettabytes upon exabytes upon Googles of information, all flowing through the internet everywhere in the world, every second of the day. Now, since the late 70s, information theorists and computer scientists have been utilizing compression algorithms to effectively reduce the size of this content to keep the internet from coming to a standstill. And this is why today we start hearing more and more about the connection between conversion rates and data sizes for applications and websites. So for example, a user may browse away from a website if it hasn't loaded in 3 seconds, or may not download an application because it can incur extra charges by their carrier. Now, savvy developers need to take control of this fact, and that means bucking the trend of just using standard compression algorithms out there. Instead, you need to start digging in deep, understanding your data, and utilizing compression in new and interesting ways to make your users happy. But fear not, young developer. I'm here to help with that process. My name is Colt McAnlis, and this is Compressor Head. In 1836, an American inventor named Samuel F. Morse concocted a way to send electrical pulses through a wire. Now, at the end of that wire was actually attached an electromagnet. Himself, along with other physicists, realized that if they could separate out the pulses of electricity on the wire to control the electromagnet, they could ring a bell every time a pulse came through. And thus was born the electrical telegraph system. You see, the entire intent of this operation was to find a way to send natural language code over great distances using a pretty robust medium. Now, of course, they needed to figure a way to devise a situation where they could take an English character, A, B, or C, and actually turn it into electrical pulses, dot, dash, dot, dot, dash. And thus was born Morse Code. The way they were able to assign this code was actually based on the inverse frequency of a symbol occurring in the English language. So for example, E, the most common occurring letter in the dictionary, actually was assigned the smallest code. The reason for this was, you have to remember, they have some guy sitting there banging on an electrical magnet, sending pulses through a wire, and they wanted to minimize the amount of work that needed to be done to communicate a message. And of course, all the other symbols on here are based upon their probability getting more complex the less probable they are to occur. Now, in modern computing, we actually use a different sort of form, and that's actually called binary code. Now, binary code is not a variable length symbol. Instead, what we say is that you're going to use a set number of bits, and then we're able to assign a symbol to a given number of bits using that static amount. So for example, ASCII assigns 8 bits to a single character. So when we get a stream of these bits on the wire, we know we can read in 8 bits at a time and determine what symbol we're actually using. Now, however, if we decided to move the other direction and implement a frequency change, much like Morse did, you see that we can actually get to something a little bit better. Now, what happens here is if we take into account the probability or frequency occurrence of the character and use that to assign a variable length bit pattern to it, we can actually start getting some interesting things. So for example, C, occurring in a given symbol stream 80% of the time, gets assigned to the shortest character a single 0. Now what this means is, instead of assigning 8 bits per character for our entire stream, we can actually assign a variable length of characters and actually end up, in this example, getting 81% savings. This is the definition of variable length codes, and it's what we're going to talk about more of today. Now, it would seem that you can't really have a discussion about compression without actually going back and talking about information theory itself. And when you're talking about information theory, you can't talk about it without introducing this guy, Cloud Shannon. Now, Cloud, who besides being awesome at parties, really good with keg stands, pretty much invented what we call modern information theory. Now, what Cloud did effectively was found that there was a correlation between information content and the probability of that symbol occurring in the stream. Now, he was able to actually measure this correlation with the logarithm function and actually get a result in the number of bits. So effectively he could find out what the information content was in terms of binary data. Now this itself was a pretty bold move that actually defined how information theory works, but for our needs, what we're more interested with is his definition of entropy. See, when you take all of the probability content and information content of a stream and sum it together, you end up with the algorithm for entropy. Now, besides being a little gnarly here, what we really find out is that entropy is actually a matching of an estimate for the minimum number of bits that each symbol has to have on average to represent the stream. Don't worry, we'll take a look at an example of that real quick. So let's take a look at this in practice. So let's say we have a stream that only has 2 symbols in it, whose probabilities are represented by P1 and P2. So you can see here that while the probability is 0.5 and 0.5 between these 2 symbols, the entropy value actually gives us 1, basically saying that we need 1 bit per symbol to represent all symbols in this stream, right? So 2 symbols, we have 0 or 1. That's pretty good. Now as we start skewing the probability, effectively one symbol starts becoming more dominant in the stream than the other symbol, so we start seeing the probability of P1 start rising and P2 start falling. We can see that the entropy value ends up at about 0.88, roughly meaning that on average, we need 0.88 bits per symbol to represent all the symbols in the stream. And this is good, right? This is where we come back to variable length codes. Some codes are bigger, some codes are shorter. To further this point, you can see that when we're really skewed down here in 0.99 and 0.01, the entropy is as close to 0 as it can get, meaning that we're going to see a lot of bias for P0 and a large code for P1. Let's look at this a bit more. So let's say we have something very simplistic here. We've got 4 symbols, right? And each one has an equal probability of 0.25. Now in this environment, the entropy is actually 2, right? So we have to have minimum 2 bits per symbol to represent all the symbols in this stream, which actually boils down to something that looks like this: 0, 0, 0, 1, 1, 0, and 1, 1, right? This is pretty much the basis of how binary works. If you know the number of bits per symbol, you can read it pretty easily. Now, to look at entropy a little deeper, if we actually start changing the probability of the symbols in the stream, we get some different results. So let's say we have a setup here where we've got 4 symbols and each one has a different probability: 0.49, 0.25, 0.25, and 0.01. When you actually run this through the entropy equation, you end up with about 0.157 bits per symbol. Again, this is on average, right? Now this means that we can start assigning variable length codes to the stream to start achieving compression, because we really can only get compression once we have differing probabilities, right? So in this case, A being the most dominant symbol actually gets the smallest code word of 1 bit per symbol, and over time we're going to end up with compression. Now remember that entropy actually represents the best estimate of the minimum number of bits required to represent the stream. And of course that also brings us into the next point, is that if you're going to be using variable length codes and get compression out of them, you need to make sure that you assign the shortest codes to the most frequent symbols in your stream. If you don't follow this principle, you're not going to get compression and you're really not going to have a good time. All right, so now let's take a look at how you actually use these variable length codes in your software to start encoding and decoding your data stream. So let's say we start with our symbol stream, ABC. And of course, we also have a symbol table. Now, a symbol table is going to map your given symbols, A, B, and C, to your given variable length code words, VLCs, right? So A goes to 0, B goes to 1, 0, and C, of course, goes to 1, 1. Now, encoding is actually extremely straightforward. All we have to do is read a symbol off the stream, figure out what code word it goes to, and then output that code word to the bit stream. So let's see what that looks like. We take an A off the stream, and of course we find that A just goes to a single 0. So we can simply output a single 0 to the bit stream. Now, of course, we take B off the symbol stream, look through our symbol table, and find that B corresponds to 1 and 0, which is pretty easy for us. We again put up a 1, and then put up a 0 as well. And of course, C, the final one here, goes to 1, 1, which again is pretty easy to do. Now, the encoding process here is actually not that difficult, as I said. We start with symbols, we move to code words, and it's done. Now, decoding is a little bit trickier though, because in decoding we effectively have to start with our bit stream and then read through and determine what symbols we're working towards. Now, here's the tricky part. because our code words are actually variable length, we don't know how many bits to read. Let's take a look at what that says. So we start with our input stream, 0, 1, 0, 1, 1. Now, we read a single bit off of the stream. We check this against our symbol table, and we realize that the first symbol is actually an A, right? A is a single 0. We got a single 0 off the stream, so we can actually put A in the output stream. Now, we read the next bit off the stream, and it's a 1. Here's where things get tricky. We don't know if this is going to be a B or a C, because you could see that both of their code words start with a 1. This means we actually have to read another bit off of the stream before we can actually make a decision about which code this is. So we read a 1 and a 0, and we can see that actually corresponds to the letter B. That means we read those off, we output a B to the stream. Now we do this again for the next one. We read one bit again, because we have to always start with the least common denominator, and we realize that can either be B or C. We read in a secondary bit and use that pair, and we realize that we've just read the letter C off of the stream. Now, this is all fine and dandy when things are working correctly, but the reality is that it's really hard to design and create the proper variable length codes. In fact, a lot can go wrong in how you're choosing what code words are assigned to what symbols, and this is where things can actually get really wrong. So let's say we end up here. We end up with the same input bit stream that we saw before, but notice that the code word for the symbol C has actually changed. It's now 101 instead of 11. So let's start decoding and see what happens. We read the 0 off of the bit stream, and we notice that that's an A. Fantastic. An A goes out to the stream, and all unicorns are happy. However, when we get to the next one, we go read a 1, and we realize that could be either B or C. Fantastic. Still things that we're doing normally. However, when we read the next 0, we're still not clear if this is a B or a C. We can't actually make a decision. It looks like a 10 should go to a B, but this might actually be a C, because if we read the third bit, we could actually make that decision. So what we're looking at here is, because of the way we've encoded our VLCs, we don't know if this 1010 bit pattern is actually 2 Bs or a C and an A. This actually gives rise to something you need to follow when designing your variable length codes, and that is known as the prefix property. Or more specifically, once a code has been assigned to a given symbol, no other code can start with that bit pattern, right? So if we have 10 with B, we should not be able to start the letter C with 10. That's going to make us have a really bad time. Of course, at this point, you have to ask yourself, where do variable length codes come from? I mean, they don't just drop from the sky into your computer for your encoding purposes. For this, we actually have to introduce someone named Peter Elias. Now, besides being a renowned tap dance fusion instructor, he also invented beta codes, or what we call today modern binary codes. Now, as we talked about, binary codes actually aren't variable length codes because they don't obey the prefix property. But Dr. Elias didn't stop there. You see, he actually constructed an entire fleet of compression codes that he used for various patterns. Now, in the early days of creating these codes, you could actually take an integer value, such as 0 through 5, and actually use that to denote what type of generation on the code you're going to have. So for instance, this is known as the unary code, probably the most simplistic variable length code that obeys the prefix property that we have. The way that unary codes are constructed is, given a specific index, you actually append that many ones, -1, to the front of it before a 0. So for example, down here at 5, you can see we've appended 4 1s and a 0. 4 gives us 3 1s and a 0. 3 gives us 2 1s, and so on. And of course, because of the way this is constructed, 0 actually doesn't have a value representation here. Now, what's important about the way that Dr. Elias actually constructed his codes were that they all were built around a specific probability distribution. So unary codes are actually optimal when all of your symbols follow a probability set forth by p to the n is 2 to the negative n. Now, if your symbols don't actually follow this probability, you're going to get a little bit of bloat in your codes later on in the stream, and you're actually not going to hit entropy. But unary codes aren't the only thing he created. Let's see here. We've also got gamma codes, right, which of course you see have a completely different construction process, and that's mainly because they have a different probability distribution down here in the bottom, as well as, let's see, delta codes are a variant of that, and themselves are actually constructed quite differently and have this monster of a probability in the bottom. And of course, we have the fabled omega code, Code, which is known to many far and wide for having one of the more complex probability distributions that you can't actually list it. It's kind of like saying Voldemort out loud. Anyhow, back in the day, the way that you would choose what variable length code to actually encode with is you would actually look at the probability of your set and sort of determine how many symbols you would have against which code is actually going to give you the optimal encoding for that set. So for example, if you had somewhere between 64 and 88 unique symbols that needed code word, you could actually find that if the probability matched properly, you could use omega codes and get the best bit pattern you needed. Of course, if you were lower than that, you may need to choose gammas, or somewhere in the middle, you may need deltas. Of course, this brings us to an interesting question. If you have a set of symbols that don't actually follow any of these known probability distribution functions, what do you do? Well, of course, the issue with that, let's see here, is that there are hundreds of variable length codes out there. You see, we've got Scallywick codes, phased-in codes, puncture codes, stout codes, Fibonacci codes, and really there's a lot to choose from. Or you can do something a little bit different and actually construct your VLCs based upon your probability directly. Let's take a look at that. In 1951, while David Huffman was still a student at MIT, he was taking an electrical engineering class where his professor gave him an opportunity. He could either write a term paper solving a very difficult problem, or he could study for his final. Of course, David, being a little bit optimized at the time, decided that he would rather solve a problem than study for his exams. Now, the problem that the professor gave him was try to find the most efficient way to represent letters, numbers, and other symbols using binary code. Of course, David decided to chomp into this full bore, and after months and months of chewing on this problem, was about to give up. In fact, he had given up and was to the point of throwing away all of his notes when it hit him. He would later say that it was like lightning striking his brain as soon as the papers hit the trash can. So what he developed at that time would later be recognized by Donald Knuth as one of the most fundamental methods of computer science and data transmission that we'd ever discovered. See, what happened was David Huffman found a way to represent and create variable length codes for any given probability in a very simplistic and compact binary tree form. Now, later he went on, of course, to figure out how to levitate things with his mind, but until then, he just used this code, which we're going to take a look at now. Now, the brilliance of what Huffman discovered was actually a connection between assigning the symbol to the code word using the table. Now, what he was able to do here was find that if he used a binary tree, he could effectively use the probabilities from the symbol table alongside the branches of the binary tree to create an optimal binary code. All right, well, let's build a Huffman tree. So typically what you're given is a set of symbols with their probabilities, and the first step in the process is to actually sort them such that the highest probability symbol is at the front of the array and the least probable symbol is at the back of the array. From here, what we're actually going to do is pop the two least probable symbols off the array and actually make them childs of a new node that's pushed in there. We actually continue this process all the way down the line, comparing the two last elements of the array together and making them children of a new value that's then pushed onto the array. Now at this point we have a fully created binary tree, and to move from this tree to the generation of Huffman codes is pretty simplistic. All we have to do is assign a 0 and a 1 to the left and right branches accordingly. To actually generate the VLC for a given symbol, all we have to do is walk from that node up to the root and record all the 0s and 1s that we trace. So for example, A, moving from its node to the root, gives us 0. B, moving from the node to the root, gives us 0 and 1. And moving from C to the root gives us 1, 1. This, effectively, is the generation of our variable length codes using the Huffman generation algorithm. And now that is a Huffman tree. Pretty easy to see that a little bit of compression can actually get you a long way. And as something as simple as statistical encoding, you can use variable length codes to actually shrink your data set. Of course, the next thing you really want to talk about is what other compression algorithms are out there that you can apply to your data stream before applying these variable length codes to actually get you below entropy itself. Of course, that's a topic for a different show. My name is Colt McAnlis. Thanks for watching.